On the noon net today, they were talking about you can have a beacon, like a signal in your car. Is that from your radio or from your cell phone? You know, where Daron, weren't you following that guy?
Sorry, I'm eating. I'm just not eating in front of you. Yes. Let me pull something up real quick here before Joe takes over.
Okay.
You can run an application on your phone that will interface with this APRS thing, or you can run a radio in your car, or both.
Okay.
Let me see if I can call this up here real quick and share it.
It was so cool to hear about that.
But a beacon is not the right term.
Okay, correct me.
Darren, tell her what the correct term is.
It's a beacon. Let Joe eat his food. That's fine. It is a position beacon.
Okay.
So this is a site in Finland that collects all the data from pretty much worldwide. And in Lincoln County, we have several sites where we collect these little transmitted beacons or packets and upload them to the internet. So this is, sorry here, try not to make you dizzy. This is me, that's my van parked at my house.
Okay.
So it knows that when I'm not moving, I only transmit a beacon every 30 minutes.
And it just does it automatically from your phone or from your radio?
This does it from my radio in my van.
Okay.
So if I start moving or driving the van, there's a smart algorithm that says it'll beacon as soon as I turn more than 30 degrees, or if I increase more than 20 miles an hour, it'll be like, oh, that's a change in what you're doing. I'm gonna increase the beacon rate. So that's what I was watching on Tad's drive-in.
That was so cool.
So as he was moving across wherever he was, down on Highway 20, that's right. So as he was coming across to here, it'd pop up a beacon with the time and his speed and altitude and his heading. And then it'd be 3 or 4 miles and he'd chunk out another one and we'd pick that up and I could see where he was along the highway.
Wow. Nice. Thank you.
Yeah, it's a lot of fun.
It requires a GPS, though, does it not, Darren?
It does, yes.
But that's often in the radio?
Correct. Where was I? Oh, this was last time I was in Reno. Beaconing from the airport there. And it was interesting to be at the air races that particular year, because as I was watching these beacons, one of the racing aircraft had the beacon in his aircraft as well. So he just making a bunch of figure eights around here real fast. It was kind of neat to see.
Now, how come you can look at this old one?
That was the last place I beaconed with that call sign. So that's my call sign -7. -9 is my van. -7 is what I use on a handheld radio, and that was back in 2022.
Okay.
Back in September the 18th.
I see that.
So you can actually search back.
Oh, wow.
I could go back here, 2021, pick the month, pick the day, and it was a busy day for me in Lincoln City, it looks like.
Oh my gosh.
But that's where I was. Oh, I went to Newport, looks like.
You could put this on your kids. If you dared.
And then I went to Rick Rio and went south down there. So yeah, you can go back years and look at your data.
Oh.
Thank you.
You're welcome.
Recap. Yeah, I'm going to recap, but I wanted to show you a couple things first. So let me go to this camera. Now, for those people who have a digital voltmeter. These cables that I've got here right here in my hand, they've got real sharp tips and they're real handy and they're about $4. So that's available. Also at the swap meet, I got that for $5. So if somebody needs a digital meter, let me know. Okay. So moving on, chapter 4B. And by the time we're done, we ought to be up to 4Q or something like that. But anyway, we're gonna stay on this until everybody understands it. All right, you probably all remember this. Static electricity. We've all walked across the room, reached out to touch the doorknob and got zapped. And that's because we've built up static electricity as we walked across the room. And when we reached out to the doorknob, which was a ground compared to ourselves, it just zapped you. And we can all relate to that. But there's something, this class and the way that the book is set up, they don't get to dealing with electrical safety. And that's what I want to deal with tonight to start with. Electricity is how we function. I mean, our bodies do not work without electricity. Now, here's something I found on the internet. This is showing a neuron, and our body is full of these. They sense touch, feel, heat. I mean, everything, and they operate at about minus 70 millivolts. Can somebody tell me what a millivolt is?
A millionth of a volt.
That's a good try.
1,000th of a volt.
Thousandth.
A thousandth of a volt. Thank you. Yes. Now, I mean, God did an amazing thing because He made us, and the inside of our body is functioning. Everything's functioning at minus 70 millivolts. And we're around power all the time. And believe it or not, up to about 40 volts, it won't even phase us. We can handle it and touch it and not be hurt. But in the last century, in the last 100 years plus, we come up with electricity here in the United States at 120 volts, a lot of the world 240 volts. Our radios, if we have a power amplifier, can have 2,000 or 2,500 volts in it. And guess what happens when you get that across these neurons?
They fry.
Yeah, you go nuts. I mean, honestly, you know what happened to me? Janet and I were on a missionary boat out in the middle of the Pacific Ocean, and I started the generator and I went down to work on a circulation pump, and she stood by to turn the generator off in case something happened. Well, I reached down and I picked up this pump, which I should have had a wire ground on, and it was grounded by being mounted. As soon as I picked it up, I was locked. And I could not break loose. And I was just going, and Janet, who there was no way she could have heard anything, thought she heard me say something, and she shut it down. And what had happened is my ring had caught a hose clamp, and I couldn't pull it off using my legs, and I was stuck. And I remember looking up. I was down in the hole, down on an engine, and the only way in was straight above me. Next thing I know is there were 4 or 5 heads looking down at me, asking me if I was okay. And I was trying to make up my mind whether I was okay or not, because it really smarted. But the thing is messing with electricity, you can't hurt yourself. But folks, 12 volts will not shock you. The only known person that's ever died at, say, 40 volts, because that's the voltage that your telephone, old landline telephones used to work at, was a worker who was working in a sewage. He was waist deep in water, and he reached up and grabbed a line, and that killed him. But it usually takes a fair amount of voltage to get that. So,
Joe, I have a question.
Go ahead.
Negative 70 millivolts. I don't understand what that means, because I thought there was 0 volts and any volts above it. Is this negative 70 in the electron flow meaning, or I don't understand that denomination.
You don't understand what's going on in the neuron, or you don't understand the level of voltage?
The level of voltage. That's right. I don't understand how a voltage can be negative unless we're talking about voltage, but negative in the sense of polarity.
Well, that is in the sense of polarity, because the outside of the neuron is positive and the inside is negative.
Okay. Thank you. That clears it up for me.
Now, in millivolts, maybe you didn't catch it, but a 1 millivolt is 1,000th of a volt. I mean, we have our batteries, our little AA batteries, AAA batteries, and they're 1.5 volts. And most of our radios run on 3 to 7 volts. And often 12 volts if it's a portable rig. But our handhelds run typically at 7 volts or so. So if that were operating within your body would quit functioning.
Yeah.
So what I'm trying to tell people, it is important to be careful what you're doing around electronics when you're working on it. If you're working on our typical 12-volt systems that we have nowadays, the amplifiers, the transceivers, the HF transceivers, the VHF, UHF transceivers, they're all operating at 12 volts. You cannot get shocked off of that in any way. The only danger with 12 volts is actually shorting it, which can generate a tremendous amount of heat. So, and I'm telling you this for 2 reasons. One is so that you understand that you do not have to be afraid of 12 volts, which most of them are around our cars and everything else. That's not a problem. And what's 2?
What's what?
I'm looking at John.
Don't do that.
2. Well, that was the main reason. I don't want people to be afraid of it. And where they should be afraid is when they're working with a tube rig or a tube amplifier, where you can have from hundreds of volts, like 700-800 volts, up to as much as probably 2,500 volts and sometimes more. So be careful around that kind of thing, and learn how to discharge capacitors. So let's go back through static electricity again. Here's an atom. We have the nucleus, which has neutrons and protons.
They're telling me that your camera's not showing your face.
No,
You don't want it to. Your camera is showing something else. I think maybe that's the camera you're on right there, maybe. Instead of this camera. Sorry to interrupt you, but Daron was mentioning it, so I thought I'd mention it.
Yeah, we don't see you, Joe, on your image there. You're either on the wrong camera or not in front of that one.
I think you're on the wrong camera.
No. Sorry, guys. Here's what's going on. All right.
I mean, it's okay. I can do without seeing your face, but Scott was saying he really wants to see your face.
Oh, well, Scott. Oh, here we go.
There we go.
There we go.
Okay, thanks,
Hey.
Joe. Yeah, now we see you. Go ahead.
Now that I'm in trouble,
Well, now let's, yeah, okay. Okay, do you see my face now?
Yes, we also see,
Yeah, and you guys see everything. Okay. I'm trying to fix this up for the recording. I wish I could explain it to you. Okay, I want to leave it like this, and some of you show up on the recording. Anyway, we have protons, neutrons in the nucleus, and then we have electrons, which are negatively charged, going around the outside. And they're little things. But if here's oxygen, which is one of the things that's in the ionosphere, and I'm going to talk about a lot of things where electricity is used tonight, because and these all relate to amateur radio, because we're going to be talking about the ionosphere, which has ions in it, and that's how we actually are able to send radio signals around the Earth. So here's a normal oxygen with its 8 electrons around it. So if we remove one of the electrons, one of the negative ones, somebody tell me what happens. No, nobody wants to tell us what happens?
Becomes a positive ion.
Ah, perfect, right. So that becomes an ion. When it's positive, it's either attracted to other atoms that are either that are negatively charged, that are negative ions, or and that's let's go on to the next slide. If we add an electron, then it becomes a, can I hear a chorus?
negative ion.
Negative ion. Well, I heard one person. These ions are what are in the atmosphere. And they're also what work in batteries, whether it's a 12-volt battery for your car, where you got lead acid in the ions that are given off in there, or a dry cell battery, AA or AAA battery. So you end up with a voltage on it. So if we go to the ionosphere, now we discussed this in some detail, and much later in the class, we will go into this in extreme detail. But for right now, the ionosphere is our upper atmosphere. It is ionized by the radiation that's coming from the sun. As the sun hits the ionosphere, it knocks electrons loose. The ionosphere is a shell of electrons and electrically charged atoms and molecules that surround the Earth. Now, on the right-hand side of that picture, you see what's called the D layer, the one that's 80 kilometers up. The E layer, that's 110 kilometers. The F1 layer, which is 200 kilometers, and the F2 layer, which is 300 kilometers. Now, the D layer, it absorbs the lower frequencies. If you're on 3.5 megahertz or 80 meters, it gets absorbed by that. So during the daytime, 80 meters does not propagate well. The upper layer, though, the in F1 and F2, the HF frequencies, say 20 meters or 15 meters or 10 meters, they enter that, they get refracted and they get refracted back down to the earth. And so by doing that, they can literally bounce all the way around the earth at sometimes, depending on what the conditions are on the night side. On the night side, the D layer is not as thick, and it permits the signals to pass right through it, enter the F layer at that time, which is not F1, F2, it's the F layer, and it gets bounced back and forth. So that's how we get our communications on HF. Now, you folks that are doing just VHF and UHF, VHF just goes right straight through this. It does not bounce at all, unless there's some extremely special circumstances, and they do occur. So another part that has a great effect on us is the lightning. Lightning is occurring all over the world 24 hours a day. And it creates noise. Every time one strikes, it creates electronic noise that radiates, just like our radio signals radiate. If you're out in the country or in a good location like Scott, you turn on your radio and you hear a bunch of and you look at your meter and it's running S3 or S5, S7. That's typically noise caused by lightning all around the earth. And so that's common occurrence that you have, and it's something that you need to deal with. By the time you get to VHF, though, it's not typically a problem. Lightning is a rather interesting thing. We're talking about static electricity, right? And it's formed as air moves up inside of a cloud. And I could not, and I'm not going to try to explain to you how it builds up the static electricity, but it builds up, and compared to the ground, it develops between 10 and 100 million volts. So if just stop and think about that. Our body operates at minus 70 millivolts, a thousandth of a volt. But when a lightning strikes, it's at 10 to 100 million volts, sometimes much greater. Sometimes it gets as much as 1 billion volts. And when it strikes, it strikes. The current, and we'll be talking more about electrical current later, but it's typically 30,000 amperes. And if you wonder what happens to a tree when it gets hit by lightning, that would explain it. So, any question on this to this point?
Sounds like God's spark gap transmitter.
Yeah, that's yeah. Well, you know, our hobby got started with spark gap transmitters, and 100 years ago, or well, maybe 110 years ago, that's all they had. And they would create a spark, and it would be hooked up to an antenna that radiate, and it would radiate over a lot of different frequencies, and everybody could hear everybody, whether you're commercial or amateur or whatever. And it wasn't, I think it was in the 20s. Scott, do you know that they came up with tubes in the local oscillator?
I think it was in the 20s, right in there.
Yeah. Yeah, so that it enabled amateurs to operate on separate frequencies, not like they were before.
Well, I
What
can
time is it,
remember,
John?
8:57 or 6:57.
Oh, okay, all right. Good, okay. Now let's talk about electricity. Electricity is the flow of electrons around a closed circuit. Now, if we're talking about lightning, most of the time, it is a static electricity building up in the clouds. But when it lets go and comes down to earth, it creates a closed circuit, which is it's rather and I'm not going to try to describe it to you. I don't know that I really can well, but it creates a complete circuit. And in this little diagram here, we're talking about electrons in motion. Notice the battery on the left side, that's a single cell. We'll call that a C battery. Anyway, the negative side is where the electrons flow from. Now you notice they flow down the wire, around the wire, up to the light bulb. Then they go through the light bulb and then continue on back to the positive of the battery. And that is a complete circuit. And so we have a power source, we've got electrons in motion, and we have a load, which is the lamp. And we can even call that a resistor, because that if you measured it with an ohm meter, it would show resistance. And the way that thing works is it gets hot enough that it lights up. So anyway, going on, here's a couple more illustrations that might help you out. I like using the water to show what's going on. Now this is a complete circuit, and I explained this before. We've got a tank of water in the top, and it's high up. And then there's a pipe coming down to a faucet. And when you open the faucet, the water runs down. And because the gravity is pulling the water down through the pipe and out the tube. Well, to complete the circuit, the water goes down the sink, out to the river, down to the ocean, gets evaporated back up into the sky, becomes a cloud, comes over, and rains over the tank on the top of the roof, completing the full circuit. So that's kind of the difficult way to get a complete circuit, but it's the same. Now, if we look at our battery here on the right-hand side, there's the negative side, and it has a lot of electrons. I heard somebody just trying to help me out here. Inside the battery is a chemical, and the chemical working with the stuff that's in the battery separates out the electrons from and puts them on the negative side. So you end up with a lot of electrons sitting on the battery. If it's not connected, nothing happens. But with this, the electrons flow down the black side through the light bulb, and then back up to the battery, which has the positive side. Anyway, let's start. Are some people starting to get a little idea on how electricity works at all? Rose?
Yes.
I'm going to ask you, Rose, are you having an understanding at all? Rose, did you leave the room?
I don't see Rose.
Yeah. How about Denise and Elise? How about you two? I see Elise shaking your head. Go ahead, unmute and tell us what.
Yes, we are getting electricity.
Oh, you are getting it. Good, good. How about Denise? How are you doing? I saw her over there to the side.
No, just fine.
Oh, good, good, okay. All right, anybody else? Does anybody have, are they not understanding what I'm talking about? Is there anybody that's in that condition right now?
You might, uh, uh, maybe it would be helpful to folks to mention something else. Because that light bulb would be like that wire is a resistance, and it's inside of a vacuum.
Yeah, go ahead, Scott, explain how a light bulb works.
So as that electricity flows through that, and that resistor heats things up, as Daron had been mentioning, then that causes that wire to glow inside, and in the vacuum it doesn't burn out. So then that allows they'll go ahead and complete your circuit. The light turns on. That's how you get light.
Very good, thank you. Okay. I'm going to show you guys this again. How many of you remember this? Here we've got a battery. And by the way, I drew that backwards. This is actually on a battery, the positive lead right here. But pretend like it's a long one over here. So this is the negative side of the battery. This is the positive side of the battery. Here's a switch that's closed. Here is a resistor, which I showed you several resistors last time. And then so the current will flow from the negative around through the wire and back through the resistor and back to the battery. But this is a wire here, and these blue beads represent electrons. So I'm going to, now, Scott, you can't answer this. You smarty. I'm going to move this electron over to here because it's attracted to this positive, which leaves a positive space here. And so I'm going to move one more time. This is negative and this spot is positive. Notice what's happening. The electrons are flowing from the negative to the positive, one at a time, like this. And it just continues. Now, what else is happening? Somebody tell me about what else is happening here. Anybody?
There's a space in between them.
Yes. And what's the space doing?
Taking up space.
It's moving to the left.
It is doing that. It's moving to the left. Yes. It's headed toward the negative. And what that is, that's every time there's a space, it's positive, right? So the positive is moving toward the negative. Every time a negative goes over, the positive gets here. Here's the negative going across, the positive here. So the positive, when the electrons are going this way, the positive is going this way. And this is referred to as hole, H-O-L-E, flow. And when you start working with solid state electronics, you will learn to talk about hole flow when you're looking at schematics. And I'll show you a schematic here later today that has a transistor in it, and it has an arrow, and the arrow points in the direction of the hole flow. So it points from positive toward the negative. All right. Any questions about that?
Yeah, Joe, what is the use in circuit design of the hole flow?
When when engineers are working and designing an electronic circuit using transistors, they often, rather than think about the electron flow, they think about the hole flow. So the hole flows from the positive to the negative. And if you're looking at a diode or you're looking at a transistor, they have arrows on them and they indicate the direction of hole flow. So it's a matter of getting your mind into gear, which way you want to look at it. Do you want to look at the electron flow, which is like this? Or do you want to look at the hole flow, which is going, the electrons are going this way, and the holes are going this way? Both are valid. And sometimes it's easier to think about hole flow when you're designing something than it is to talk about electron flow. Back when there was tubes, electron flow was all you wanted.
So hole flow is conventional, Joe?
Yes, I believe that is true.
Because we tend to think of positive going to negative. So that's the conventional flow?
Yes.
Okay.
Oh, that was so well put. Darren. Yeah, that is considered conventional. And if you look in the, I don't have it.
But this is
what-
interesting to me. When you talk about conventional, I'm not familiar with that term. What do you mean by that?
Well, I always learned that, or the way I learned it was that the current moved from the positive terminal to the negative terminal of the battery, which is the conventional way we look at circuits. So you apply that, you build that circuit, and the current goes from the positive side to the negative side, which is actually the way the whole flow is working. In reality, the electrons are moving the opposite direction, from negative to positive.
I'd never heard that before. I had always heard that electrons went from negative to positive and not the other way around. I've never heard of hole flow, and that's really interesting to me.
Yeah, I think it's just a different way of understanding it, and I guess it works. I mean, however you theorize it or view it doesn't really matter too much, I don't think, in design, so long as you understand how it actually happens at the nuclear level, I guess. But you will see referenced conventional current flow, I think.
Yeah, just while we go through the class, I will tell you if we switch to conventional. Darren, do you want to explain what you got there on your?
I was just, you wanted chip resistors, Joe. That's all I had there.
Yeah, do you have something a little pointed so you can point them out?
Yeah, if I could see them, I would.
Well, I see
There.
the size of the
I wanted to give you the size of the pencil to show you. That right there, the little black thing is either a chip capacitor or a chip resistor.
The black one is a resistor, and the one next to it is a capacitor.
Correct. So there's just for size comparison with the pencil. And just so, this is a soldering iron with a very small tip. So you can imagine having to remove that, heating up both sides and lifting that little teeny chip out of there is a little bit of work.
They have special heating irons that heat, and they're like tweezers, and they heat both sides, so you can reach in and grab it and lift it off.
Yes, if you're spoiled, that's the tool you use. I totally agree.
I'm spoiled. Or you can heat up two soldering irons and heat both sides at the same time and remove it.
Or you can use something like this. Just like that.
Okay. Darren, here we've got a schematic. We've got a battery over here. We've got a switch. And we got 3 resistors. Now these resistors are in somebody.
Series.
Series, right. So, and I'll just say this is a 100 ohm. And this one's 100 ohm. And this one's 100 ohm. Now, what is the R total?
300 ohms.
300 ohms. Okay, and this is a battery, and this is the positive side, and this is the negative side. So somebody tell me where all the electrons are built up.
Negative side.
Correct, correct. And we have the positive side. So the electrons are going to they're going to circulate around this direction. So since this is positive, if we've got an electron here, it will be drawn over here, making a hole, which will attract the next electron, which will move this direction. And then we'll have a hole here. So here we have an electron that's attracted in this direction, and it just continues on around. So the electrons, which are here, and there's all kinds of them, they start flowing down the wire this direction. They come down here, they come around this corner, this being a conductive wire, right? And they go through the resistors, through the switch, and back to the battery. Does anybody have any problem with that concept? I hear no problems. I'm going to call this a 5-volt battery. Although I don't know where there's any 5-volt batteries, but because we have a power supply that produces 5 volts. Would somebody like to tell me how much current? This is current. This right here is the electron flow through the wire and through the resistors and through the battery. So the current is going that way. It's also called I. We're working our way.
1.5 milliamps.
Pardon?
1.5 milliamps.
Could be. How did you figure that out?
Just 300 or 5 divided by 300. Not scientific, just trying to remember the old Ohm's law.
That is correct. I, which is current, is equal to E or V over R. So if you want to know what I is, you take E or V, and pretty soon I'm going to show you guys a whole bunch of helps on this. Some of them call it E, some of them call it V. E is for electromotive force, which is measured in volts. And when I was young, it was I equals E over R, and nobody used V's. But people learned over the years that people understood V as volts. So that is 5 volts right here. So let's say that we'll draw this over here, and we can put 5 here. And what is R?
300.
300 ohms. So that is equal to, anybody got their calculator? See, 5 divided by 300 is equal to 0, 0. And there's
0.0166.
0.0166.
Correct.
Okay. If it were 1.000, that would be 1 amp. But since it's 0.0166, if we go, there's a 1/10 of an amp, 100th of an amp, 1,000th of an amp. What is 1,000th of an amp?
Milliamp.
Well, yeah.
Milliamps. So if we change this from amps to milliamps, oops, wait a minute. Small m, big A, right? That would be, you move the decimal point over 3 points, this becomes 16.6 milliamps. And that's the current, the number of electrons flowing. Does anybody remember how many electrons flow through a circuit to create an amp?
1 coulomb?
Correct. How much is 1 coulomb?
Oh, it's a lot.
Here it is. I was off by 1 order of magnitude. Last week, I was saying it's 10 to the 19th. 6.24, and actually this digit here went 6.24 and then went on for about 8 more digits. But it's 6.24 times 10 to the 18th electrons to produce 1 ampere. That's a lot of electrons. Is it?
Yes.
Does everybody understand what 10 to the 18th means? Let me explain it to you. 10 to the first equals 10. 10 to the second, that's 10 times 10 equals 100. 10 to the third equals 1,000. You follow that? That's 10 times 10 times 10. 10 to the sixth equals 1 million. Now notice there's 6 zeros. Okay.
Mhm.
So 10 to the ninth is a billion. Get this on end of the screen. 10 to the 12th is a trillion. 1 0 0 0 0 0 0 0 0 0 0 0 0. This is 10 to the 18th. 18 zeros after it. That's a lot of electrons. And that's about actually I think that's less than our national debt right at the moment, but I don't know. Okay, moving on. Now that we can see this, now here's something I want you to see. Current comes out of the battery, goes through the wire, through all the resistors, through the switch, and back to the battery. This is a closed circuit. If you open the switch and break this right here, all current stops flowing. Now, shortly we're going to take a break. And when we come back, we're going to have Daron give us a few illustrations. Now, here we are, we've got a battery, plus and minus, so we're going to call that 5 volts. And we got here 100 ohms, 100 ohms, and 100 ohms. Now, we got a whole bunch of electrons over here that are going to flow this direction. Can somebody tell me where they're going to go?
All places equally.
That is correct. Absolutely 100. Part of them will come and go this way. Part of them will come and go this way. And then part of them will come and go this way. And because each one of these is 100 ohms, the current will equally flow through each one of these resistors. And then they'll come back up here and they will join So the current coming out here is the same as the current coming here. So the current that comes out of the battery comes and then splits up and goes through these three resistors. And then it comes this direction through the switch and back to the battery again. So the current I on the low side and I on the high side, I low equals I high. But the current going through the resistors is different.
I can't see your formula. Can you raise your sheet a little bit?
Oh, thank you.
Thank you.
So what you have is you have the sum of the current that's going through here, and through here. And they add up. So if you take I equals E over R, which is equal to E, which is 5 volts. It's 5 volts from here to here, 5 volts from here to here, and 5 volts from here to here. And you divide it by the resistance, which is 100 ohms. So we end up with 5 divided by 100. So we got point and we got 0, 0, so 0.05. That's 50 milliamp or 0.05 amps that are going through each one of these. So you got 0.05 amps here, 0.05 amps here, and 0.05 amps there. How much current is flowing right here? Somebody?
Roughly 15.
0.015.
Point. No. Scott, I think you're wrong. It's 0.15. Not right? Yeah. 0.15. Not sorry, Scott. So this is divided into 3 parts. What is the current at I on the high side right here?
The same as the low side.
0.15.
0.15. So what happens is current splits up. Part of it goes this way, part of it goes this way, and part of it goes this way. But the current coming out here, they all add back up and come out here. So the current here is the same as the sum of each one of all of those. Time?
1 minute.
Okay. Now, is that you, Darren, with the 0.90?
Yep, 9 volts and 0.16 milliamps
Oh. Okay.
through the circuit.
Okay. Let's take a break.